Okay, so let us now discuss the conversion of the transfer function to state space. And this is the derived transfer function of the simple circuit example 1 that we are discussing. Please note that the illustration of the transfer function is our system with transfer function s squared over s squared plus 4s plus 1 over 6 is representing or modeling the system, and the input is Rs and the output is Cs. And so in this case, the VLS over VIS will be Cs over Rs. To convert transfer function to state space, we need to separate the numerator and the denominator into two separate subsystems. And we will start with the uh, denominator part. And so this system will be breakdown into this. So 1 over s squared plus 4s plus 1 over 6, we're in the output, we call that x sub 1 of s, and the input is still the rs. And for the second stage will be the numerator of our transfer function, which is s squared. It's understood that the denominator is 1, and this time the input will be x of 1s and the output is cs. And solving for this first stage, then the transfer function in the first stage will be x of 1s over rs, and that will be 1 over s squared plus 4s plus 1 over 6. Okay, so we're now going to solve the transfer function for the first stage muna. Okay, so solving the equations, no? We're going to cross multiply this equation, so rs times 1, and then this polynomial multiplied by x of 1s. Okay, so eto na po sila, no? Yan. And so that will be s squared times x of 1s plus 4s times x of 1s plus x of 1s equals to rs. Okay, then after this, we're going to take the inverse Laplace of this. Note here that what I did here is a shortcut method, no? Because we know that if we're going to take the inverse Laplace of, say, s squared, x of 1s, that is equivalent to the second derivative of x of 1 of t. So by the way, there is a correction here, no? Yan. So it should not be s, it should be t. No? After taking the inverse Laplace, it will now be x of 1 of t. But note here that, as I was saying, that the inverse Laplace of s squared will be the second derivative of x of 1 of t. And so by notation, we've been using double dot for the second derivative and a dot, no, for the first derivative. Okay, so the for 4 we copy 4, and then the inverse Laplace of s, x of 1s, will be the first derivative of x of 1 of t. Or by symbol, we use x of 1 dot for the first derivative. And the inverse Laplace of x of 1s is x of 1t, and the inverse Laplace of r of s will be r of t. And note also, as we have written in the previous discussion, that the second derivative of x sub 1 is equivalent to x sub 2 dot. Okay? So, and then the x sub 1 dot, it is equal, no, or equivalent to x sub 2, no, in our notation. I hope you have seen this pattern in our PowerPoint presentation. I have shown you this, no, wherein the x sub 3 will be equivalent to uh, x sub 2 dot, no? And x sub 1 triple dot will be equivalent to x sub 2 double dot, or that will be equivalent to x3. Okay, anyway, I have this in our PowerPoint lesson. So now, uh, from the derived equation here, okay, we we have here x sub 2 dot, and if we're going to transpose the other terms to the right side of the equation, then we will get x sub 2 to be x sub 2 dot to be negative x sub 1 dot negative 4 x sub 2 plus rt. Okay? Nakaligtaan kanina yung 1 over 6 dito, no? So, please take note na may 1 over 6 from here. Now, writing this in vector matrix form now is, uh, let's go back for a while. Let's pause. Okay. So, writing the vector matrix form, x sub 1 dot, x sub 2 dot. So, that is 0, 1, 0. So, that is 0, 1. And then 0 here. Okay, yan. Okay. So, and then writing the, here we have 1 over negative 1 over 6, negative 4, and 1. So therefore we have negative 6, negative 4, and then 1. Okay. Now if we're going to solve the second part, no, which is this one, s squared over 1. So taking the transfer function of this second part will be cs over x of 1s cos s squared over 1. So cross multiplying cs times 1 and then x of 1s times s squared. So we're going to have this. And after that, taking again the inverse Laplace of this. So the inverse Laplace of cs is ct. The inverse Laplace of s squared is x of 1s. Second derivative, no? By the way, this should be t, no, not s. Okay, so if we're going to correct that, this should be t. Okay. And take note also that as we have derived from the previous slides, that x sub 1 double dot is equivalent to x sub 2 dot, which is equal to negative 1 over 6x1, negative 4x2 plus rt. And therefore, our output yt, which is equals to the ct, which is ct is equals to x sub 1 double dot, which is equal to x sub 2 dot, is also equal to this. Y is equals to negative 1 over 6x1, negative 4x2 plus rt. Okay? So, therefore, the derived state equation, state space equation model will be this one. Okay? So, x1 dot, x2 dot will be equal to 0, 1, negative 1 over 6, negative 4, okay, plus the b, which is equals to 0, and actually it's 1. No, if you recall from earlier, it's 1, no? Not 1 half. Okay, and the output equation is this one. So y is equals to negative 6, negative 4, and then okay, so let's correct this. Likewise, this is equivalent to 1, no? That's 1. Okay,